Okay, so we just talked about angular displacement and how that's actually circular distance around the point, creating a circle. And we use radians to describe the length of a circle equal to the length of the radius. The next thing we talked about in straight line or one-dimensional mechanical or mechanics dealing with motion was velocity. And we said velocity is the change of distance over the change of time, and it's the same as speed except it has direction. Well, if you ever think about an object going on a circle, it's constantly changing direction, so that is definitely a velocity. What we're going to do here is we're going to look at, in terms of angular distance or angular displacement, how we define the label and how we figure out the formula for finding velocity, angular velocity. Well, since velocity is the change of distance or change of time, it would make sense that angular velocity is the change of angular displacement with time, and that's what we have right here. And the symbol we use for displacement is theta, like angle theta. We use that a lot in trig and calculus. And then delta t is the change of time. And the label in SI is going to be radians per second. And then we can change radians per second to meters per second for what we call a tangential or one-dimensional velocity away from the circle, going a straight line away from it, by just multiplying by the length of the radius over 1 radian, and now you have meters per second. So we're going to be doing that here. So let's take a look at this. So like I said, just regular velocity is change of distance over change of time. That means that angular velocity, this is a lowercase omega. You might recognize uppercase omega, which is this, but this is the lowercase omega. And this is equal to the change of, instead of distance, is this angular displacement, which we said is theta, over the change of time. And like I said, the SI unit here is in radians per second. So the example that we use in our script there was, suppose that we have 12,500 RPMs as an angular velocity going around a spinning object, like in a centrifuge. So we want to know what we call the period of revolution. In other words, how many radians per second is that going to be? So we're going to rewrite that as 12,500 revolutions over 1 minute. Just to get the fractional view of conversion here. Okay, so that's how we're going to start this problem. So 12,500 revolutions over 1 minute times, and we're going to change revolutions to radians. So this is going to be 1 revolution on the bottom and 2 pi radians on top, times fractionally. Now we got revolutions out, we got radians, which is what we want on top. So now we have to change minutes to seconds. So that's pretty easy. Minutes on top and seconds on bottom. And then 60 seconds per 1 minute. And the minutes cancel out, and that does leave us radians per second when we multiply this thing out. So if you do, you'll find that it's 262 radians per second. And if we're going to translate this to tangential velocity, then we're going to ignore the pi, just include that as part of the calculation here to get the 262. I suppose you could leave it in that form if you wish. I believe it's something like 250 pi over 3. Radians per second. either way, again, it's fine, but since we're going to go tangentially, I'm going to use that number right there. Now, so the next part is imagine an object on a string being whipped around that fast. Now, 12,500 revolutions a minute is pretty stinking fast. But just imagine having, and then the outside force, the pull on the string as the object tries to pull away at that speed is pretty intense. So there's a good chance that string is going to snap. And when it snaps, according to that video that we saw, it goes off in a straight line. A straight line off of that circle is called a tangent. So we call that a tangential velocity. Okay, so I'm going to find the tangential velocity. I take that 262 radians per second. I'm going to put that over 1 second just to give it the fractional form. And then I'm going to convert that over to meters per second. Okay, now the one thing about this is we said that the diameter of this was 10 centimeters. Well, diameters don't help us. Rad, as you can see the word radian pretty much there, you need the radius for the radian. So we're going to say that the length for 1 radian then, instead of being 10 centimeters, it's going to be 5.00 centimeters. Because the radius is half the diameter. But, but we want this in meters per second. So we got to change centimeters to meters. And since centi means 100, this will put 100 there, and one is the meter is the larger label of the two, so we put 1 there. And then we just go ahead and calculate this out. This comes out to 13.1 meters per second. And so that's going to give us somewhere in the neighborhood just short of 30 miles per hour. So yeah, it's pretty fast for an object spinning around a point. So that's really all there is to this. There's not a whole lot more to this. We'll get into more complicated stuff in the next couple of sections. But in the meantime, the practice problem on page 261, 18 through 26E. Have fun.